do work or supplying heat. We are saying a chemical potential energy is the energy stored within the structural and units of chemical substances. Like if you look at methane, for example, there is carbon to hydrogen bond, and that bond requires energy to keep it together. So that energy which is stored in that chemical bond is actually what we call the chemical potential energy. Then we are talking about the difference between the amount stored depends on the arrangement of the atoms, and then how the atoms are arranged determines also the amount of energy that is stored in this bond. For example, we talk of carbohydrates being energy-giving foods. It's just because in carbohydrates, there are so many carbon-hydrogen bonds, and each of them carries an energy, which when broken, maybe during respiration, releases a lot of energy that is stored in their bond. And this is basically because both hydrogen and carbon have very small atomic radius. And because of that, they are tightly attracted together and therefore capable of storing large amount of energy. And then all the energy in the process can be accounted for as work, but there are those ones which cannot be stored, and such energies are always released as heat, and that is what we can measure. Now, the law of conservation of energy, you are aware, which states that energy can neither be created nor destroyed, meaning that under all circumstances. Good afternoon. Good afternoon.
Good afternoon, sir.
Can you identify yourself fully? You are?
It is Rothomio Godwin.
Okay, Rothomio. Then Pesh, can you identify yourself? Pesh, can I hear you?
My name is again Patience.
Okay. It's fine. Then we can continue now. So we are saying energy can neither be created nor destroyed.
Again, no patience.
Okay, you are loud and clear. You can mute now. So we are saying that energy can neither be created nor what? Destroyed. So in that essence, there are only changes, chemical changes that may affect chemical reactions. Some of those reactions may result into production of energy, especially if the energy stored in the bonds are higher than the energy that is being used to break the bonds. So in that circumstance, the enthalpy change, if it is high, is likely to be negative. Negative means that excess energy is removed, and therefore it is expedited in the atmosphere as the overall change in energy. We talked about the heat, which is the energy transfer from one object to another, and it is reflected by the temperature difference. By the way, Margaret, what do you think is the difference between temperature and heat? Margaret?
Temperature,
yes.
It is the degree or intensity of heat present in a substance.
The intensity.
Whereas,
okay.
Whereas heat It is the form of energy that is transferred between objects with different temperatures.
Okay. Again, no? Is it possible to measure heat? Fish? Okay, Godi. Is it possible for us to measure the heat that is stored in the bonds, in chemical bonds?
I'm not sure about that.
Okay. Can you tell how much energy you gain when you eat a half a kilo of posho? You're not sure?
Yes, sir.
But you are the people who tell us that carbohydrates are energy-giving foods. So how do you know it has given you energy?
I use the amount of energy that it gives.
Okay. Again, how do you know that posho has some energy stored in them?
Teacher, I think when the posho is broken down in the body and it provides energy, that's when you start to know that there is energy in that posho.
How do you know it, that there is energy?
I think after the posho has been broken down in the body and then ATP is found from that part. ATP is got from the posho that you have eaten, something of.
Again, no, can you know now ATP is being produced? How do you know that ATP is being produced? Okay, now members. Huh? Yes? You were saying something?
Teacher, I was saying,
Mm.
yes, I was saying that when maybe after the carbohydrates have been broken down in the body, and then ATP the energy is got through ATP. Then I was thinking that through that form, energy is got through carbohydrates. That's what I was thinking.
Okay, it's actually hard for you to know that now I've eaten ATP is being produced. But of course, you can see it from your physiological reactions. Sometimes after eating, there is sweating, meaning that excess energy is being produced. Sometimes you are physically weak, but eating maybe 2-3 hours, you gain that energy that had been exhausted. You really find that physically you are stronger. So all those are evidences that maybe after eating food, that energy which was exhausted in doing work is now being given. When you are sweating, it is also an indicator that excess energy in form of heat is being given. Sometimes even you tire after eating, you feel so sleepy and meaning that there is some energy being used in breaking down that food substance that you have. That is just the brief issue about it. Now, it is very easy for us to measure the temperature because the temperature, we just use the thermometer and we see the rise in temperature, and then we say, okay, it is hotter or the temperature has fallen or something as such. But in reality, it is not possible to directly measure heat. So when we are to talk about heat, we say is the transfers, the energy that is transferred from one object to another because of the temperature differences between them. Look at point A and B. My assumption is that point A has higher energy than point B. But because of the difference in the temperatures, you'll see that heat will flow from A to B. So that means that B, which was colder, becomes warmer. Of course, the temperature will not exceed that of an A where it is coming from. At all times, we need to balance because that amount of energy will not be increased or reduced. The amount of energy will remain the same. Just like I told you some time back, when you supply a certain amount of energy, a fixed amount of energy to heat 1 cup of water, and then another one, the same amount of energy, let's say the charcoal, you need it to heat 10 liters of water. Definitely, the 1 cup of water will boil faster. Why? Because the amount required to heat, that total amount is transferred to a smaller volume of water, and therefore its temperature will rise faster, and therefore that water will boil as faster. So whenever two objects are in contact, you'll find that the heat will keep on being transferred until eventually those two bodies have the same amount of energy or amount of heat, and that is measured in joules. So we said in chemical reactions, sometimes the reaction can be exothermic, sometimes it can be endothermic. And we are saying that in endothermic reaction, there is heat flow into the system. Endo means taking it inside. And because of that, heat is absorbed. And therefore, the amount of heat is greater than 0, and it is depicted by positive change. For example, when ice melts, that obviously means that heat is gained. And that means that it's going to be reflected by change in the temperature of the environment. Just hold an ice cube in your hand. You'll find that eventually your hand becomes colder than it was before. Why do you think it is getting colder? Because the heat that was in your hand is being transferred to the ice to ensure that that ice melts. So as the temperature of the ice block is increasing, yours is decreasing until you reach a point where there is an equilibrium. The amount of heat in your hand equals that of the ice. Then there will be no net heat transfer. So any reaction in which heat is absorbed or in which heat flows into the system is called endothermic reaction. So I've talked about melting of ice, sublimation of mothball. We talk about heat used to cook. You can see someone roasting the chicken, meaning that the chicken is actually gaining the heat, while that heat that was in our charcoal is getting consumed. So during endothermic phase, we are saying that the energy absorbed does not increase the temperature because the energy is being used to overcome attractions between the particles. Remember, in order for them for a chemical reaction to occur, there must be bond breaking. First of all, bonds must break, and then eventually new bonds are formed. So that energy required to cause the break of that bond cannot be deflected in terms of the temperature rise, because the temperature cannot rise because that energy is not actually increasing the kinetic energy. That energy is just breaking the bonds. And once those bonds are broken, then a chemical reaction can take place. So we are saying that for endothermic reaction is usually accompanied by fall in temperature from the surrounding. The temperature of the surrounding usually falls, and then the temperature of the system increases until equilibrium is got. What about endothermic reaction? In endothermic reaction, it is an indicator that actually the amount of energy stored in the bonds is greater than the amount of energy supplied. For example, if you have your charcoal, you apply very little energy, you ignite your charcoal. Then once the charcoal starts burning, it produces the great amount of energy, which overpowers that heat that you had in your matchbox that lit the charcoal. Now, because of that, you'll find that in exothermic reaction is usually accompanied by rise in temperature. And of course, that rise in temperature will be mean that a lot of energy is being generated. So example of that is combustion of fuels, then cooling of the skin from perspiration as water evaporates, then freezing of water is also an exothermic reaction. Of course, when water is to freeze, it means that you will remove heat from it so that the temperature falls. That's why when you have a fridge in the house, you'll realize that inside your fridge will be very cold and iced. But when you go back at the pipes behind, it is too hot, meaning that some heat has been withdrawn from the water or the fruits you have put in your fridge, and then eventually it is transferred to the coils that you have at the back of your fridge. So all exothermic reactions involve heat flowing out of the system, meaning that the external environment becomes higher. And then that is a result of the bond formation. So we talked about temperature being a measurement of the average kinetic energy of particles, and it is only detected by a thermometer. You can measure this one directly, but you cannot measure heat using a thermometer because heat is measured as the product of the mass of the substance you have used, of the specific heat capacity of the substance that you have used, and then of the change in temperature. So the change in temperature is always dependent on the mass and the kinetic energy of the substance that is under consideration. Now, just think about this. You have two identical candles like I've talked about. You're using it to heat 2 samples of water. One sample is a cup of water and the other one is 10 gallons of water in a drum. The question is, how will the change in temperature of the samples compare? Number 2, how will the amount of heat received by each container compare? Godi, can you hear me?
Yes, I can hear you.
So if you have 1 cup of water and 10 cups of water, and you're using the same amount of heat to heat them, which one do you think will have a higher temperature rise?
Come again?
I am saying, can you see what is on the screen?
I can see it.
Okay. The first scenario is, if you have 2
Yes, teacher.
candles, you can see the candles. One is heating a cup of water. Another one is heating 10 gallons or 10 cups of water. The question is, which one do you think will boil faster? Can I get a response? Okay, let's take the scenario home. At home, sometimes they tell you that the visitor has come, the visitor wants to go, and you are making tea for everyone at home. But the visitor is saying, I'm going away. Doesn't your parents tell you, please first put 1 cup of water so that that visitor gets the tea? That is exactly what I am meaning here. That when you have a smaller amount of water and you're using the same amount of heat, the overall change in temperature is higher because that heat is easily distributed into that water and therefore it becomes higher. But when you have a large volume, let's say like 10 liters, definitely that same amount of heat is going to be distributed throughout the 10 liters, meaning that the overall change in temperature will be low, yet the same amount of heat is produced. Because remember, the heat is the product of temperature change, the product of the specific capacity, and then the mass. So the higher the mass, the lower the change in temperature, because at all points, the amount of heat remains the same. Is it okay, Godi? Are we there? Yes, Margaret, you are on and off. What's the problem? Can I hear you?
Yes.
What's the problem? You are on and off.
Share the network.
But you move out. For you, you like staying inside the house. Pesh?
Yes, teacher.
Pesh, you are also in the house. Find somewhere where the network is stable, even if it means outside the house. Get your pen and your book, and then you move. Because it is bad to be where sometimes you miss, sometimes you are getting. Okay, so we have said that when you use that candle to heat 10 liters of water, by the way, after the candle is blown off, if you put your hand, you may realize that nothing has changed. The temperature is almost the same. It doesn't mean that that water has not absorbed the heat, but it is only an indicator that that heat produced is distributed through the whole gallon of water, and therefore very little change in temperature. But remember, the same heat, because the mass is higher, then the temperature is lower. When the temperature increases, it means that the mass is lower. But remember, the amount of heat that is produced is mainly dependent on the mass or the volume of the liquid which you are heating. Now, temperature is actually the measure of average kinetic energy of particles in a matter. And we are saying the greater the kinetic energy of the particles in a sample, the hotter it feels. And therefore, it is important for us to differentiate between heat, because heat may be the same, but the temperature increase will be dependent mainly on the size or the amount or the space in which that heat is distributed. Now, we are looking at heat at temperature still, and we are saying the energy absorbed or released as heat in a chemical reaction or physical change is measured by a calorimeter. I think we talked something briefly about the calorimeter. Now look at that drawing where we have fuel, which that fuel might be paraffin, could be alcohol, could be petrol, and then we have a vacuum in between. I hope you're able to see that vacuum. In between, we have a vacuum. Now that vacuum is air-filled, such that you minimize heat loss. And then we have the water component and the thermometer. Now, when we light that fuel, let's say paraffin or what, it is going to heat the can of water. And remember, the volume of water must be known. Once the volume of that water is known, and then we measure the temperature rise, and then we know the specific capacity of water, then definitely we are going to find the total energy absorbed by that water. Now that energy absorbed by water is because some fuel has been burnt. So we also take the measure of that amount of fuel burnt. That amount of fuel burnt will actually have given us the heat that is taken by that water in that can. And because of that, let's say it is ethanol. And initially we had 46 grams of ethanol. Then after heating, we remove and we discover it is 5 grams. Then we are now saying that 5 grams of that ethanol has produced that heat. That heat is measured by as a product of mass times the specific capacity of water times what? Times the change in temperature, which is measured by the thermometer, and it will give us the overall heat. Then if we want to get the heat of combustion of ethanol, then we convert it to 1 mole of that ethanol, which will now be 46 divided by 5 times that amount of heat that we have got. And that is basically directly how we measure the amount of heat. Any question? Or I'm too fast? Are we still there?
Yes.
Yes, Godi? Godi, ask a question or a comment. Yes? What? I can't hear you well, Godi. Please unmute and talk because I've not heard. Margaret, are you with me?
Yes, I'm with you.
Okay. So you look at that scenario. So the SI unit of heat and energy is in joules, and a joule is defined as the heat rise of a temperature of 1 gram of pure water by that degree Celsius, that temperature. 1 joule is equivalent to 4.184 joules. That is given as the standard joule, and that is also the specific capacity of water. So the heat capacity is the amount of heat needed to increase the temperature of an object by exactly 1 degree Celsius. Of course, different compounds have different heat capacities. Water is taken as a standard because 1 gram of water exactly raises the temperature of 1 gram of water by 1 degree Celsius. And that's why it is taken as our reference. So it is dependent on the mass of the substance you are heating. It is dependent on the specific capacity because specific heat capacities always vary. Then the quantity of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius is also called a calorie. Sometimes we measure the amount of heat by calories. For example, we have 10 grams of sugar giving us 41 calories, meaning that 10 grams of sugar releases 41 kilocalories of heat. And that means that if it is completely burnt or it is completely digested in order to produce carbon dioxide and water, every 10 grams of sugar you take, you actually get 41 kilocalories, of which is actually a lot of energy. But for us, we take a lot of it. Now, we look at specific heat capacity, which is the amount of heat which is required to raise the temperature of 1 gram of a substance by 1 degree Celsius or by 1 Kelvin. Remember, on both Kelvin scale and Celsius scales, the rise is the same. Although for Kelvin scale, we add 173 as our starting point. So specific heat capacity, therefore, is the measure of a substance is a measure of a substance, ability of a substance to store heat. That means that a compound with a very high specific heat capacity stores a large amount of heat compared to those with very low specific heat capacity. Water has an abnormally high specific capacity because of what I was trying to explain to you. I told you that water, their bonds is in form of hydrogen bond. Okay, Pesh, I can see your message, it's fine. Now, some of you were part of this, and that's why it becomes as revision. But those who are not there, in case I am fast or in case there is something not clear, please put up your hands. My assumption is that we have some basics and we are running through. So I was trying to say specific heat capacity refers to the amount of energy required to increase 1 gram of water. Yes, Godi?
Teacher, can you start from from that point of temperature?
Yes.
Because that was a bit
weird. Godi, what do you think temperature?
Yes.
What do you think temperature is?
So as you see that it's the average kinetic.
Okay. Go then put off your mic. So we are saying temperature is the measure of average kinetic energy of particles in a sample of matter. And we are saying the greater the kinetic energy of the particles in a sample, the hotter it feels. I just give you a simple example. As you run, when you increase your speed, the chances are high that you also increase your kinetic energy, isn't it? And you'll find that a person becomes even much hotter if the person runs faster. A lot of sweating, a lot of heat is generated by that person. That means that that increase in kinetic energy is depicted by rise in the temperature. And like I have told you, that temperature can be measured simply using a thermometer, but the heat produced is actually a product of that increase in temperature times the specific capacity of the component you are heating and then the mass of a substance. Now, I have said that temperature is measured by a thermometer, which could be in Celsius scale or in the Kelvin scale. But heat cannot be measured in that way. As I was trying to explain, that the simplest way to measure the heat is using a calorimeter. Now, this is an example of a calorimeter. A calorimeter is a simple component. Let me show you something. Is a simple component where you have a heat shield. The heat shield here is a fuel shield. Then you have the source of fuel. The source of fuel here could be anything you want to measure its specific capacity. It can be paraffin, it can be alcohol. Then there is a vacuum here. The purpose of this vacuum is to prevent any heat loss by conduction and convection. Then you have a water component with a thin-walled can. Now, what you do is you measure a certain amount of water, a known volume of water, let's say 1 liter, and put here. Then you close it well and then cover. The whole of this is to prevent any heat loss due to conduction and convection. Then you light up this. Now, once you light up this, we assume that all the heat that is being produced by this burning fuel is actually transferred to the water component. Once it is transferred to the water component, we are going to have this water component gaining some energy. The moment it gains some energy, its temperature will rise. The rise in temperature here will actually mean that this water has gained energy. So that temperature times the specific capacity of water, because we know it, and then times the mass of water. If you had put a half a liter, it means that it is 500 grams, will be the total heat gained by water. And we are saying heat lost by the burning fuel is the same as heat gained by water. Now, after we have got this heat, then we come back to the fuel chamber. You ask yourself, how much fuel had I put at the beginning? Then how much change is that? That means that you're going to weigh your fuel before burning, then you weigh it after burning. So of course, after burning, that fall in mass indicates that that is the amount of fuel that was burnt. And it is that amount of fuel that has caused the rise in heat, as we have calculated by the mass, specific capacity, and the temperature rise. Now, if you've known how much fuel was burnt, then you can actually get the amount of heat that would be produced if 1 mole of that substance. Remember, 1 mole has a mass equivalent to its relative formula mass. Good, are we there? Good, is that okay?
Yes, sir. Yes.
Okay, Margaret, are we together?
Yes, we are together.
Okay. Then that is what we were talking about when I talked about the difference between the temperature and heat. Let's look at what I was talking about, specific heat capacity. I have said that different components have different heat capacity. Remember, C or P is the specific heat capacity at a given pressure. Q is the energy lost or gained, and then M is the mass of the sample. Now, delta T is the difference between the initial and then the final temperature. Therefore, change in heat or specific heat is calculated as the mass of a substance times the specific capacity times the change in temperature, which actually we call MC theta in most cases. That is how the physicists called it. So I have just given you here samples of some molar capacities of some elements. Like pure aluminum has a specific capacity of 24.2, which is actually much higher than water. Remember, water has a specific capacity of only 1 gram per mole. Argon has 20.8, helium has 20.8, iron has 25.1. So water will have an abnormally low specific capacity. And I've explained this one, that because water has a high, has a hydrogen bond in between its molecules, and therefore makes it hard for water to be, that bond to be broken such that water is released for boiling. Now, I want you to do this calculation. Get a pen and a paper, and I want to find the answer. A 4.0 grams sample of glass was heated to this, from this to that. A temperature increase of 40.4 Kelvin was got and was found to have absorbed 32 joules of energy as heat. What is the specific capacity of the glass? Then how much energy will the same glass sample gain when it is heated to 314, from 314 to 344 grams? Get a pen and a paper and do it, then you tell me the answer. I think this should take us about 4 minutes. Godi, are you with me?
Yes, teacher.
Pesh, are you doing it? Now Pesh is quiet. Margaret?
Yes, I'm doing it.
And Pesh, why are you quiet? You don't have a pen?